Okay, we're going to take a couple of those thermodynamic processes we sort of just introduced in the last mini lecture on thermodynamic processes and look at the equations for work. So we were talking about how the work is related in some processes to the change in internal energy and others to the heat, but what does the work actually look like? So we're going to use an example where we have an isothermic, so no change in temperature, isothermic process, where the volume can change. So when we introduced the isothermic process in the mini lecture on processes, we talked about a piston in a container. So that's kind of the example to be thinking about. So if I can do work on that piston, how will that look? So isothermic, that means the change in temperature is equal to 0 and volume is allowed to change. And that's important, right? Because if PV is a constant and volume can't change, pressure can't change, so we don't really get any change. All right, so we know in an isothermic that the heat is equal to the work done by the system. So what is that work related to? All right, so let's kind of go through this derivation just to introduce you to how we use all of this information that we've gathered in terms of the way gases and pressure and volume and temperature and energy behave to derive our situation of work done by an isothermic process. Okay, so we know that in general, the work is equal to the force dot dl, right? And we also know that force is our pressure times our area. Okay, so this is just back in our kind of first semester work and energy situation. Keep in mind that our A dot dl is really a representation of our volume, right? So I can rewrite this as my d work is equal to dV times the pressure. Sorry, forgot about the pressure there. And this fundamentally is what is going to be important for us. Now, if I want to know how much work is done through a change in volume, I take the integral of both sides. So the integral of dW, of course, is equal to the work, is equal to the integral of P dV from my initial volume to my final volume, or for volume A to volume B. You'll also sometimes see that as. Okay, now the other thing we want to keep in mind is when we're dealing with an ideal gas, we know that PV equals nRT, right? We know that PV equals nRT. And so P is equal to nRT over V. I'm just solving for V. So let's pop that in here. So that leads us to the integral from the initial volume to the final volume, so across the volume change of nRT dV over V. Well, nRT, of course, is just a constant, so I'm left with the integral from the initial volume to the final volume of dV over V. Well, and what's that? That, if I take that integral, we have the work is equal to nRT times the natural log of V final over V initial. So this becomes a very important relationship for us. This is the work done by an isothermic process. Okay, the work done by an isothermic process. All right, well, what if I have an isovolumeric process? Let's look at that one. So an isovolumeric process, keep in mind that the volume doesn't change. Let's look at what that work looks like. two processes we sort of mentioned at the end of the last mini lecture. Their implications on internal energy are through the work. And so we'll look at what work looks like for an isovolumeric process. All right. Okay, so in this case, we have no change in volume. Okay, so there's no change in volume. Well, if I don't have a change in volume, the natural log of 1 is 0, and so I have no work done. So no work. No work is done. Another way we can think about that is that my pressure times my change in volume is 0. And if change in volume is 0, my pressure times my change in volume is what we knew the work to be. Remember, the work was equal to the integral of P dot dV. Well, if there's no change in volume, this also equals 0. So anyway you want to think about it. With a isovolume process, no work is done by the system. Okay, so that one's kind of an easy one. What about an isobaric process? So remember, an isobaric means that the change in pressure is equal to 0. All right, so what happens with an isobaric process? We're going to use our same integral. If the work is equal to the integral of the initial volume to the final volume of P dV, and pressure is constant, that means it's P, the integral of V initial to V final, of dV, and that's just P times the change in volume. So the work done in a isobaric process, so no change in pressure, is P dV. Now, we're going to look at it in two ways. One, just pressure, if I know the pressure times the change in volume, but if we remember that the pressure, again, this is in our situation where we have a temperature, then the pressure, remember, was nRT, and this is going to be the temperature at wherever we're ending up, times 1 minus V final over V initial. Okay, so this is another way we can write the work done in an adiabatic process. I'm sorry, in an isobaric process. So these two are going to be important for that. So this is isobaric. This is isothermic, where volume can change. And no work is done, and volume obviously is changing here too. No work is done in a situation where volume cannot change. All right, so let's maybe do an example. Let's do an example of what this